record to the cloud, yeah.
Okay, it says recording in progress. I think that should be working.
Thank you.
Okay, so yeah, a gentle introduction at times, and then towards the end, I'll touch on a few more advanced topics. And what I'm going to do basically is introduce Gaussian processes in 2 or 3 different ways. We may not get through it all, that's fine, but we'll get through the kind of basic introduction to things. So if you have any questions, please just put them in the chat. So I probably won't have time to click on the chat, but if Maurizio or one of the other hosts could keep an eye on it, and I'll try and pause at times and just interrupt me if there's questions that should be answered as I'm going. Okay? And I'll pause for questions at various points. Okay. So, well, normally we'd be welcoming to Sheffield, of course, but we're not. So let's just get on with things. So to start with, we need to think, before we think about Gaussian processes, we need to think about Gaussian distributions. Okay, so we'll talk about the distributions, which you've probably studied at school a little bit, talk about some of their properties, and then we'll see how they can be generalized quite easily from multivariate Gaussians all of a sudden to an infinite dimensional Gaussian, and that is what we call a Gaussian process. Okay, and then I'll move on to some kind of motivations and derivations for why we might use Gaussian processes in our work, why they're a useful tool, and then finally some of the difficulties. But you'll see much of this material will be repeated by Nicola in his second introduction after the break. Okay. So Gaussian distributions, bell-shaped curve. You've nearly all seen these before, okay? Normal distributions. So we've got a classic shape, and they're specified by a mean, which I'm going to call mu here, and a variance, which I'm going to call sigma squared. So the mean determines where this curve is located. So here it's centered around 0, it's mean 0. And the variance determines its spread, it's sigma squared. Okay. And we know how to write down the probability density function, the PDF for Gaussians. We get this classical e to the power of y squared, essentially, minus y squared, essentially. So with the mean subtracts from it, so we get y minus mu squared, and we scale by the variance. So you can see as the variance gets bigger, you're going to need a bigger distance between y and mu to matter, okay, and vice versa. The density function, the distribution function, the cumulative distribution function, which is plotted here. Okay, so this is a probability that a Gaussian is less than some value. It's not known in closed form, but we have very good approximations to it. Okay, so why are we so interested in Gaussians? You know, Gaussian processes, generalized Gaussian distributions. So let's just think about what's so nice about Gaussians. So first of all, you know, they're just convenient mathematically. They kind of occur in a wide variety of situations, and they're easy for us to work with. So one of the key properties that we're going to make use of today is that the class of normal distributions is closed under linear operations. So what do I mean by that? I mean, we can add 2 Gaussians to each other, and it's still a Gaussian. We can multiply a Gaussian by a constant, and it's still a Gaussian. When we get to Gaussian processes, we can do things like integrate them, differentiate them, and so on, okay? And they will remain within the family of distributions. They'll remain Gaussians. Okay? So that's a nice property mathematically. It means that we can make progress on paper with things in a way that we can't for many other classes of models. Gaussians occur frequently in nature, of course. The central limit theorem says that if you look at a sum of a large number of random variables, or the mean of a large number of random variables, that generally they will converge towards having, that mean will converge towards having a normal distribution. Okay, so they are a natural family to consider in many cases. Then there's some facts that you might be less familiar with. So if anyone's come across this MaxEnt, maximum entropy approach to statistics and machine learning, you know, there's these fun facts like that the Gaussian has the maximum entropy of any distribution with a specified mean and variance. So the principle behind the maximum entropy principle is that if you don't know how to model something, you should pick the distribution with the largest entropy, the most amount of uncertainty, essentially. So if you know the mean and variance, the distribution with the largest entropy is a Gaussian. Okay. They're infinitely divisible. If there's any probabilists here, you know, various things. So other nice properties, like if they are jointly normal and they're uncorrelated, that implies they're independent. Okay. So uncorrelated implies independence for jointly distributed Gaussians. And that's not true for many or perhaps any other random variables, classes of random variable. And finally, lots of the procedures that we use in statistics and machine learning have interpretations as Gaussian models. So for example, in statistics, you probably studied least squares regression. So the idea there is you got data Y, you want to fit a regression model like this, where you've got some parameters beta that you want to estimate. One way of doing it is minimizing the sum of squared errors. So this is a very kind of common way of fitting models. Now that is equivalent to assuming a Gaussian error term. Okay, it's equivalent to fitting a model that looks like this probabilistically and using maximum likelihood. So these Gaussians appear all over the place. They're a nice, tractable family to work with. We should study them a little bit. So that's univariate Gaussians. What are multivariate Gaussians? So again, if you did maths as an undergraduate, you'll have seen all of this before, of course. Okay, but what we mean by multivariate Gaussians is two or more random variables that typically co-vary. Okay, they're correlated typically. So we talk about a vector y, a random vector y that is in Rd, so of length d. And we say it has a multivariate Gaussian distribution, and we'd write things like y as a normal distribution or Gaussian distribution, and often you see people put a subscript d here to indicate a dimension. Okay. And all we need to specify still is the mean, but now the mean is a vector because the random variable is a vector, so the mean is a vector, and the covariance matrix. So the covariance matrix of a vector of length d is a d by d matrix. So that's all we need to specify for a multivariate Gaussian. It's mean vector and its covariance matrix. And we'll see how this carries over to processors in a moment. So in 2 dimensions, again, very simple. If we've got the mean, it's just a simple vector. The covariance matrix we can understand to be the diagonal terms or the variances here. So the variances of the individual elements of our vector, so y1 and y2. The variance of just this univariate y1 is sigma squared 1. And the cross terms here, the off-diagonal terms, are the covariances. And the covariances are the square root of the variances, the product of the variances, times the correlation. Okay. So it's a nice structure that we can understand what these numbers mean, as long as we understand what covariance and correlation mean. Okay. And again, we can write down the PDF probability density function that has a nice squared exponential shape. All fine. Okay, so let's just see some pictures, and we'll generalize from these pictures to Gaussian processes. So these are 2-dimensional, multivariate Gaussian distributions. So what I've got here is a cloud of points. Each point is a 2-dimensional vector. Okay, so each point is a sample from my multivariate Gaussian distribution. And my distribution, I picked it to have mean 0, 0. So it is centered around the origin here. So that's the point in the middle. And then we've got the covariance matrix, which I just picked to be the identity here. So each variable has variance 1, and they're uncorrelated. You can see this is a circle shape here. There's no correlation between these two variables. And if I just project all these samples onto, say, the y-axis and draw a histogram, I recover my bell-shaped curve. Okay, so this is one of the properties we're going to see, is that the marginal distribution of Gaussians is Gaussian. And similarly, if I project onto the y1 axis, the x-axis here, I get another Gaussian. Okay. So let's change these numbers a little bit. Let's change the mean. Okay, so if I change the mean from 0, 1, it just shifts the cloud up. Okay, so it was centered around 0, 0, it shifted it up to 0, 1. And if I change one of these variances, so the variance of the y-axis, I've changed from 1 to 0.2, so you can see the cloud is shrunk. So we now have a less of a spread in the y direction. But the off diagonals here are still 0. They're still uncorrelated. So y1 and y2 here are still independent, essentially. Okay. So there's no relationship. If you told me y1, it wouldn't give me any information at all about y2. Yeah, it wouldn't help me predict y2. Okay, so now we've changed things again. So now I've introduced a correlation here. So in this covariance matrix, I've got variances 1 again, but now I've pushed the covariance between the two variables to 0.9. And you can see what's happened here. Instead of a circular or a cloud, okay, or a squashed circle, we've got an ellipse. There's a correlation here between y1 and y2. So if you now told me the value of y1, if you told me y1 was -2, I would have a good idea about the value of y2. Yeah, I would know it probably isn't positive. For example, it's probably less than 0. The one thing just to know is that the marginal distributions, the histograms on the side here, haven't changed at all. Yeah, they look exactly in the previous plot because they're still marginally normal 0, 1 random variables. It's just now they're correlated. Okay, and we can scale these things. It just shrinks the cloud. If I put a factor of a third here, it just makes the cloud less spread out. Okay. And if I really ramp up the correlation to a big number here, 0.99, knowing one of the variables is essentially equivalent to knowing the other one. Okay. If you tell me y1, I now know y2 to very good precision. Okay. And the higher this correlation gets, the more true that becomes. Okay. So that's in 2 dimensions. Each point here is a point in 2-dimensional space. It's a vector of length 2. So what happens if we go into more than 2 dimensions? So to help us think about this, I'm going to plot the previous plot slightly differently. So here I had the scatter plot of the points in 2-dimensional space. Each point has a value of y1 and a value of y2. Okay. So I'm just going to plot it slightly differently. Instead, I'm going to plot it as 2 points, and the first value here is the value of y1. So that's what I've called index 1 here. Okay, so if we're looking at this, this light blue point, so the first value of y1 was 1.2 or something, so it's 1.2 here, and the value of y2 on this axis was 1.3-ish, and so that's what we get here. Okay, and I just join them with the line. So each pair of points is still a single sample here from my 2-dimensional Gaussian. So it's just, this is a sample. So this top line is a sample, the blue line's a sample, black line's a sample, so on. So this is just 2 indexes here. We've got index 1, which I plot on the x-axis, and index 2, which was previously plotted on the y-axis. Now I've just plotted them next to each other. Well, let's have 5 points now. So I'm going to think about in 5-dimensional space. So my main vector is going to be a vector of zeros still. And I picked a covariance matrix that looks like this. Okay. Now, each of my samples is a vector of length 5. So this top sample is 5 points in R. Okay, so a single vector in R5. And I just joined the points to indicate that they're all one sample. So each little curve here is a single sample from my 5-dimensional Gaussian distribution. Well, that's 5 dimensions. Let's go up a bit. So let's have 50 dimensions. Okay, so here I've got the mean vector again. It's all zeros. The covariance matrix is given by a 50 by 50 matrix like this. And I just plotted all these points in a line with their index here, so 0 to 50 along the axis here. And these are the values of those variables. And each line is a single sample. So you can see what this is starting to look like. These look like functions. And this is how we think about Gaussian processes. We just think about them as functions, or another way of thinking, they are an infinite dimensional Gaussian distribution. So instead of having just 50 indices here, typically we'll have an infinite number of values it could take. Okay, so a continuous index. So all we need to do to generalize from these Gaussian distributions to Gaussian processes is to change this index here from a finite set to a continuous set of indices. So let's just think about this, and I'll pause for questions once I've given the initial definition. Okay, so we want to think about Gaussian processes. So what is a stochastic process first? So a stochastic process is just a collection of random variables indexed by some other variable. Okay. So we've got some index set, curly x here. Then my process, y, we could just think of it as a function, y of x. So for every index, little x, in my index capital X, there is a random variable associated to it. Yeah. So curly x could be the integers 1 to 50, like here. Okay, so my index here is 0, 1, 2, 3, 4, 5, 6, 1 to 50. Or it could be something else. Okay. It could be the real line. it could be R2, it could be whatever. Okay. So we just think about stochastic processes as a set of indexed random variables. Okay. So typically, the variables are in R, the index set is a subset of Rn. And we think of it as a function. So the key thing to note here is that if the size of your index set, if the number of elements in it, the cardinality of it is infinite, then Y is an infinite dimensional process. There's an infinite number of random variables in this set if there's an infinite number of possible indices. And that's what we're going to be interested in, this situation where there's an infinite number of indices. So how do we study stochastic processes? Well, thankfully, all we need to study processes is to think about the finite dimensional distributions. So in other words, for any finite set of indices, so if you pick n values of the index, so x1 up to xn, then all we need to know is this law. Okay, so it's like a distribution function. So you need to be able to specify something about any finite set of random variables. And if you can do that, Kolmogorov showed, we know completely the law of the stochastic process. Okay? So all we need is to be able to specify something about the finite dimensional distributions. Okay, so that is general stochastic processes. How do we move to Gaussian processes? Well, a Gaussian process is just a stochastic process where all the finite dimensional distributions are Gaussian. So in other words, if I pick a finite set of variables from my big set of variables, then they will have a Gaussian distribution. And in particular, they'll have a multivariate Gaussian distribution with some mean and some covariance matrix. Okay. And that's all there is to it. Okay. We think about Gaussian processes as an infinite collection of random variables where, if we look at any finite set of them, that finite set has a multivariate Gaussian distribution. Okay. So this makes Gaussian processes easy to work with because all we need to know how to manipulate are Gaussian distributions. And you learned about them when you were an undergraduate and maybe even when you were at school. Okay. They are very well understood distributions. So we typically write things like y dot, okay, and I write y dot here to indicate that y is a function. We write y dot twiddles GP to indicate that y is an unknown function and we are giving it a Gaussian process distribution. Okay, so yeah, GP, sorry, Gaussian process. Okay. So quickly, are there any questions at this point? I think that's a good point just to pause. Let's have a look. Questions. Oh no, no questions in the chat. But if anyone has any questions, please just ask them.
Richard, there is one question in the Q&A.
Oh, I found it. Yeah, by Randall. Thanks, Matt Randall. So the question is, can mu and sigma depend upon n? Okay. And yes, absolutely. Mu and sigma will depend upon n, but more importantly, they depend upon x as well. Okay, so we'll get to that in the next few slides. So the choice of index here is going to change our mu and our sigma. Okay. Okay, so if there are no other questions, let's get straight into that then. So let's have a look at how to pick those things. Okay. So just remember, for a Gaussian distribution, we only need to specify the mean and the variance. Yep. This is for a distribution, the mean and the variance. To specify a Gaussian process, we need to specify the mean and covariance functions. Okay. So rather than being fixed vectors like they are for distributions here, they now become a mean function and a covariance function. Okay. So y of x is a random variable. Yeah. One of our family of our random variables, and the expected value of yx is just m of x. Okay, so the mean of it is m of x. And the covariance between y of x and y of x prime, so if x and x prime are two different indices, the covariance between these two random variables, y of x and y of x prime, is just given by the covariance function, which I'm going to call k here. So it's k of x and x prime. So that's typically how we specify them. We can do it in other ways. This is typically how we're going to specify them. So the mean is a function of x, and the covariance function is a function of x. So I have not told you how to pick m and k here. I've just told you that we need to pick an m and k. So what do we do? And this is where the kind of the art and the skill with using Gaussian processes comes in. Okay? So in your computer software, whichever software you're using, you typically have to specify the mean function, although it's often assumed to be 0, and the covariance function. And those two choices determine how successful your model is going to be, whether your model is going to represent reality or whether it's going to be a terrible model. And there's some rules we have to follow. Okay? So the mean function here is straightforward. We can do pretty much whatever we want for the mean function, and you don't get in any trouble. You can let it be whatever form you want. So typically in machine learning,
sorry, Richard.
Yes.
Paulo is asking something that is probably needs to be answered now.
Okay. Yes, please.
In the chat.
Oh yes. Okay, Paolo. What does X stand for? Okay. So yeah, good question. I'm sorry about that. So X is just my index here. So it's a free variable. So if you're modeling distance against time, X might be time, for example, or whatever it is you're modeling. But mathematically, we can think of it as this is a function of X, the X-axis here. So it just tells us where along here we're doing. It's indexing our set of random variables. But what it is will depend upon your situation. Okay? So just think of it as the input to your function at the moment. Gaussian processes are models of functions of X in this case. Oh, sorry, you asked me what X prime stands for. Sorry, thank you, Jean-Paul, for clarifying that. So yes, yeah, thank you. It's so difficult without being able to interrupt verbally. But so X prime here is just another value of the index. Yeah, thank you. So if X is one of the indexes, X prime is another index. So I could have had an X1 and X2 here. Okay. So in terms of this picture, okay, if X is the value at 10, say, and the index, the X prime is at 11, then that would be the correlation between the random variable at 10 here and the random variable at 11. So it's just given the index between the two of them. Okay, great. Any other questions? Just keep them coming in the chat. Okay, so there's a question from Ala about how can we compute the expected value and the covariance of a GP if it is a stochastic process of an infinite number of parameters. Yeah, that's a great question, Ala. So let's just go back to those slides. So I've not said anything about computing the mean and covariance here. We are specifying it in advance. So it's going to be one of our modeling assumptions. So we're going to assume something like, well, let's assume a prior mean of 0. And then we're going to use the kind of the calculus, the probabilistic calculus of Gaussian processes to update that mean to get a new picture of what that mean function is. But to begin with, we need to pick our best guess at what the mean function is. And our best guess, if you're in machine learning, is typically that it's 0 everywhere. In statistics, it's more common perhaps to do something parametric here, to have like a linear regression term or something more complicated. But often it's best just to start out with 0. Okay. So that's the mean function. There are very few rules about how we pick the mean function. The prior mean function, this is. Okay. The covariance function is more complicated. So the covariance function, we typically let this be just a function of the indexes again. So the covariance between y of x and y of x prime. So that's two different values of my random process. We let this be a function of x and x prime. And the key property we have to satisfy here is that k has to be what's called a positive semi-definite function. Okay, so that's one of these technical criteria that mathematicians like to write down. But what it means in practice is that it's got to lead to valid covariance matrices. So if we pick any n of our random variables, so if we pick n indices, x1 to xn, If we write down the covariance matrix, which is often called the gram matrix, okay, then that's got to be a positive semi-definite matrix, which just means it's the analog of being positive for a single number, positive eigenvalues, essentially. Okay. And this criteria that it has to be positive semi-definite is what causes us all kinds of headaches in modeling. It means we don't have a completely free choice about how we pick K here. We are limited to a fairly small range of kernel functions, and it can cause us problems in the computation, and it's hard to determine if a function is positive definite and so on. So because this is difficult to do, it tends to limit us to a small class of covariance functions that we work with most of the time. Okay, well, there's a question in the Q&A. So Dev, your question, I will get to that in a moment, okay? What's typical for the covariance? Well, let's get to that in a second. So one of the typical assumptions we make about the covariance is that it's a stationary, okay, which means that the covariance between y of x and y of x prime is just a function of the distance between x and x prime. So that means that, you know, if you look in this bit of space, that tends to look on average in distribution the same as if you look at some other bit of space translated somewhere else, a priori. So before we see any data, we expect every region of space to have the same kind of distribution. And it's a stationary process. We sometimes, or this is a much stronger assumption that is done less often, but we do sometimes assume that the covariance function is isotropic as well, which says that it's just a function of the magnitude of the difference between x and x prime. Okay. So it doesn't matter which, it's the same in all directions. You know, if x here is a two-dimensional variable, it doesn't matter if you head up north or east, we expect the same kind of variation. Okay, we'll think about that in a moment. But the key thing to take home about the covariance function is that it determines the nature of the Gaussian process. It determines the flavor of the Gaussian process. Your choice of covariance determines what your model looks like, what the space of functions is that we're working with. Okay, and again, Takafumi, I'll come back to your question later. So let's just look at some pictures. Okay. So someone asked about what the most, what's a common choice of covariance function. This is the RBF, the radial basis function kernel, or it's sometimes called the Gaussian kernel, which is a terrible name for it, or sometimes called the squared exponential or the exponentiated quadratic kernel. But the key parts of it is just the distance between x and x prime squared e to the power of that. Okay. So this is by and large the most commonly used covariance function. We can talk about the merits of it later, but this is what people most commonly use. And what I've plotted underneath here are just random samples from a Gaussian process, a zero mean Gaussian process, with this covariance function. So each line here is a function, and it's a random function from my Gaussian process. It's one sample. So you can see, that they are centered around zero. They have zero mean on average, but that any one curve may be far from having the zero mean. This yellow curve up here doesn't go below zero, but the collection of curves has mean zero. Okay. Now it's very hard to know, and it's very hard to understand what this covariance is going to change these curves. So the best thing we can do is play around with changing this covariance function to see how it changes these curves. So we've got e to the minus half x minus x prime squared here. If I now instead I divide by 0.25 squared, what's happened to the curves here? Well, instead of varying slowly over this period, they now vary much faster. So this number here and the denominator is called the length scale, and it gives a characteristic length over which the functions vary. So here the length scale was 1 essentially, and so the curves vary over a distance of length 1 on the x-axis. We think, informally what we say. Here the length scale is 0.25, and so the curves vary over distances of about 0.25. One more. If I make the length scale 4, now the functions vary much slower. Yep. By the time the length scale is 4, they're starting to look like constants almost over this range. And they vary very slowly indeed. Okay, so this number here, the denominator, is typically called the length scale. It determines how wiggly the curves are, essentially how fast they vary as x changes. The number at the front here we can also change, and that just scales the whole variance. Remember, k gives the variance between y and x prime. Okay? So if I put 100 out the front here, all we do is stretch this y-axis. So we've gone from varying between -3 and 3 to varying between -30 and 30, because I've multiplied the variance by 100, or changed the standard deviation by 10. Okay? So these curves are still mean 0. They still have a length scale of 1, but now the variance is 100. Okay? The standard deviation is 10. Okay, so that's the RBF kernel, the radial basis function kernel. One thing that, one property that we might talk about later about these covariance functions is that the curves that you generate from this RBF kernel are infinitely differentiable. Okay, you can differentiate them 1 times, 2 times, 3 times, 4 times, so on. Okay, they have derivatives of all order. They are analytic functions. That makes them incredibly smooth functions. Okay? It's so smooth, in fact, that if you knew their value at one location and on all the derivatives, you'd know the value of the function everywhere. Okay, they're analytic functions. So often we want to use models that aren't as smooth as this. So one of the popular families of covariance functions that I use are the Matern family. Okay, and the Matern family typically come with some index. So this is the Matern 3/2 family, and it has this form. And these curves, these still have the same length scale here. It's got a length scale of 1, and it's got a variance here of 1. But now these curves are only 1 time differentiable. You can differentiate these once, but not twice. Okay. So they are mean square differentiable of order 1. So another kernel here, this is Brownian motion, which you probably have studied at some point. So the covariance between x and x prime is the minimum of x and x prime. So this is our first non-stationary kernel here. It matters where you are in space. That you can see all the curves start from 0 and grow out. And these curves are nowhere differentiable. Whatever point you look at here, the functions are not differentiable. And they're also infinitely variable. You know, this is Einstein's model, or related to Einstein's model of how points move around, particles around. They jitter back and forth all the time. Okay? So nowhere differentiable, very rough functions. Okay, this kernel here is a white noise kernel. So this says that the correlation between x and x prime is 1 if x equals x prime, and it's 0 otherwise. So what does that mean? It means that if we look at these functions, if we look at a point, each variable at any point has variance 1. But if we look at 2 neighboring points, no matter how close, they are uncorrelated. So this is, we get what's called the white noise process here. Okay, this is just a wall of sound, if you like. Okay? There's no correlation in this picture at all. And there's some work to make this precise. We think about this as being the derivative of the Gaussian process, the Brownian motion, or in other words, the Brownian motion is the integral of a white noise process. Okay, any mathematicians will be hating me right now. Okay, but that's kind of how you can think about these things. Okay, so questions at this point. So a question from Dev, what's a typical covariance function? Well, typical is probably a matern, an RBF, and typically what we do, we put 3 parameters in these things. So you'll typically have a length scale and a variance, and we'll estimate them from the data. But that doesn't, just because it's typical, that doesn't mean it's a good thing to do. Okay, we can try more sophisticated things, but typically start with matern, 3/2, 5/2, and work from there. So then there's a question from Jesse and another one that's related from Takafumi about, do we have to standardize training data to a mean 0? That's never a bad idea, I would say. Okay, often, standardizing your data to be mean 0, variance 1 before you start helps, okay? But you don't need to at all. It's not necessary. The reason I say it helps in the sense that we're going to, when we've got 3 parameters in these things, we need to estimate them from the data. And that estimation process is a difficult optimization. And if you've centered your data to be mean 0, it gives the optimizer a good idea about where to start looking. Whereas if your mean in the data is around 1 million, your optimizer has got to get from wherever you started out to 1 million, and it might not always be successful in doing that, as we might see in a minute. Okay. So yes, it's a good idea, but definitely not necessary. So Mike Donnelly says, what's the benefit of functions being differentiable? Well, differentiable relates to being predictable, right? Now, if you know the value of the function here and its gradients, you have a very good guess where it's going to be a little while later. Whereas with Brownian motion, if you know the value of the function is here, that's all you know where it is currently. It doesn't tell you what direction it's going or anything. So, you think about the direction of a ball being thrown through space. It's useful to know where it is in space, but if you also know the direction it's going, that's more useful. And if you know the rate of change of the direction, its velocity, it's more useful still, and its acceleration, and so on. Okay. So the more information we have, the easier it is to predict. So if your underlying function you're modeling is smooth, then it can really help to assume that. If it's not smooth, it can be harmful to assume that. Okay. So it's just to help with that, with the modeling, really. Okay. So there's a question about, should I expect kinks in a sample? Well, that depends upon your sample, right? From the Gaussian process, it will be, if you pick a continuous covariance function, your functions you generate will be continuous. Okay. If you have a white noise term, or if you have a jump, a discontinuity in your covariance function, you can get discontinuous samples. You will get discontinuous samples. Okay. And whether that's appropriate to your modeling situation depends upon what situation you're in. Okay. So as a question from Felix, isotropy is only relevant for multivariate GPs, right? Well, we've only talked about, okay, I know you're speaking, okay. So yes, it's only relevant when X is, all the pictures I've had so far, X has been the real line, okay? We could also have X being a subset of Rn, and so isotropy is only relevant when the dimension of X is bigger than 1. Yes, sorry, I should have made that clear, Felix, thanks. Simon asks, is there an equivalent formulation for GPs to stochastic differential equations? Yes, there is. That is somewhat beyond what I'm going to talk about today, but Whittle, for example, showed that a long time ago, Peter Whittle. So in particular, these matern families are what you get if you think about Ornstein-Uhlenbeck processes, okay, OU processes, and you could consider them as the continuous time or continuous space analog of autoregressive processes. But yes, it's beyond this kind of introductory talk. But yes, there is a formulation of many Gaussian processes as stochastic differential equations, but not all. So the RBF, I don't think you can write down, for example, as a stochastic differential equation, but you can for these maternal ones. The Markovian ones, essentially, you can. Cesar, we'll get to your answer in a minute about why would we use white noise. I will come to that in a moment. Okay. And again, the anonymous question about what scenarios can white noise and Brownian motion be applied to, we'll get to. But if you think about Brownian motion, it's the model of all the stock market modeling. You know, so the Black-Scholes model for pricing options and calls, that's based upon Brownian motion, for example. So, you know, if you think about Brownian motion, it says tomorrow is going to look a bit like today, but we have no more information than that. You're just modeling as a continuous function. That's about all you can say for it. Okay. So Al says, can we build a kernel empirically based on data? And the answer is to some extent. Okay. So we typically put 3 parameters in the kernels, okay, like variance and length, and we estimate them. But it's very hard to estimate the entire functional form here based on data. And the reason that is difficult to, you know, have a non-parametric model here is that the answer you get at the end has to be a positive, definite function. And it's difficult to make that idea work. I dare say there's lots of research on it, but yeah, I don't know the answer to the top of my head, but good question. So Dongwei says, if we choose one type of kernel and find that the covariance matrix is not positive definite, what can we do with it? Does it mean that the kernel chosen doesn't match the smoothness of the function? So the kernel, you know, whether the covariance matrix is positive definite, it's just a function of the kernel. It doesn't depend upon the data at this point. I told you nothing about using data here. Okay. If you find your covariance matrix is not positive definite, it means you've used an invalid kernel. Okay, so you need to go away and use a valid kernel. The one exception to that is that we're doing all this as a computer and numerical errors can grow very fast. Okay. So sometimes, particularly with this kernel, the RBF kernel, you don't need too many data points until you get numerical errors that start to make your matrices not look like valid kernels anymore. Okay, so we can run into problems, but generally, if your covariance matrix is not valid, it means your kernel is not valid. Okay, Cosmo asks, X can be 2-dimensional input. Yeah, absolutely. Okay, and we'll get to that. X can be a 2-dimensional input, 3 dimensions, whatever. Okay, and it doesn't need to be a subset of Rn either, but nearly always is. Okay. Batsala asks, X axis is unit 5. However, seen that as an infinite index. Yes, that's right. Okay, so I think I understand what you're asking about, Batsala. So here I've just drawn it between 0 and 5, but this is a continuous, you know, this is, think of this as the subsection of the real line, the interval of the real line from 0 to 5. So there's an uncountably infinite number of values between 0 and 5. Okay, so yes, the index here is all the values along here. Okay. Oriel asks, how do you sample from Gaussian processes in practice? Do you discretize the space and generate n-dimensional Gaussians? Yes, it's exactly what you do. Okay, so to do these plots, I took a value every 0.01, I think. Okay, so I split this into 500 values along here. I form the mean vector, which is a 0 of length 500, and the covariance matrix, which is a 500 by 500 matrix, determined by this. And then I just use the multivariate normal command to generate from it. Okay. Yeah, good question. Okay. So about how we choose the kernel, I'm going to delay that. I think Nicola's going to talk about that later, okay? And I'll talk about that briefly at the end of the talk if we get there, okay? Ollie asks, can the choice of kernel itself be a hyperparameter? Say you have a bank of kernels available and you train an outer learning task to automatically pick the kernel which yields the best result. Yes, absolutely. Okay. So you, to get technical for a moment, once you've fitted a given kernel, you get the marginal likelihood. And if you fit many different models with different marginal likelihoods, you could pick the model that had the highest marginal likelihood, or the model that did best on some test problem. Okay, so if you split your data into training and test set, you could fit multiple different kernels and then predict on the test set. And so there's work on AutoML, automatic machine learning, so the automatic statistician project and so on that does things like this, and you can combine kernels in an automated way and all sorts. Okay. Barbara asks, is it possible to model a function that have a smooth behavior in one region and rough behavior in another region? So yes, it's definitely possible. Whether you can do it simply with a single kernel, I'm going to say I don't know the answer to that, but often what people do is use the treed Gaussian process. They partition space. So they might say in this region of space, my function is very smooth, I'm going to use an RBF kernel. In this function, it's very rough, I'm going to use a Matern or a Brownian motion. And then your fitting problem becomes estimating the kernel and where to partition space. Now, I suspect there are kernels that will do something like this for us that are non-stationary in that sense. But again, it becomes really hard to work with them. Okay, really hard to find good non-stationary families and hard to predict. Zeal asks if we have an empirical covariance matrix, is it a valid thing to minimize distance between empirical and functional covariance matrix with the least squares method? Well, that would be a way of fitting. Okay, so we've not talked about how to fit Gaussian processes yet, or how to fit any model. You might be a Bayesian and just have to do things the Bayesian way. You might be classical statistician and like doing it by maximum likelihood. You might like doing it by cross validation. Okay, or we could use the Zeal method and try and match the empirical covariance matrix to the functional covariance matrix. That is a valid way of fitting a process. I've not studied that method. I don't know whether that would be a good method. I don't know whether it would have all those nice properties that we know about, but it's a thing you could do. Yeah, and it wouldn't necessarily get you in any trouble, but I don't know if it'd be a good idea or not. Okay. Wow, what a lot of questions. Okay. Just one more from Juan then. What is the meaning of 3/2 in Matern? Yeah, I didn't tell you that, did I? So the Matern family is a family that's indexed by some value, which I've not given you in full here. Okay, so this is one element of the Matern family. Okay. Now, the Matern family is very, it's a complex form, except when these are fractional half powers. So 1/2, 3/2, 5/2, 7/2. Then they have a nice form like this. So I've not got the slide with that information in. It might be in Nicola's talk later. Okay. But typically we use these half powers. So Matern 1/2 is nowhere, it is a not differentiable covariance function. 3/2 is once differentiable. 5/2 is twice differentiable. Okay. And as that index increases out to infinity, it converges to the RBF kernel. Okay. So yeah, I've not told you the information to answer your question properly. One. Okay. Yeah, I think that's right, Mike. I think I'll move on now because I do want to cover the thing. There's an open session later, and I'll have more time for questions later. But let's make sure I cover the basics before I run out of time. Okay, so let me carry on with the slides, and we'll pick up all your questions later. There's plenty of time for questions in the coffee break this afternoon in the open roundtable discussions. Okay. Thanks though for the questions. It's incredible. Okay. Okay. So I've said some of these things in the chat, but just to re-emphasize them, that the Gaussian process here inherits its properties from the covariance function. So how smooth it is, the variance of it, the differentiability of it, all comes from this covariance function K. So I always think it's useful just to really understand one covariance function well. So here I've got the covariance function K of x prime. It's just x times x prime. X is one-dimensional here, so I don't need this transpose, but if it was a two-dimensional value, you need an inner product. Okay, so just think of it as x times x prime, and these are the functions, the random samples generated here. So what's happening in this picture? Why does this kernel lead straight lines through the origin? Why is that happening? Well, we can see this very simply here. Let's suppose our model. Let's have a model of straight lines. Let's suppose that y of x is c times x, where c has a normal 0, 1 distribution. Okay, so forget Gaussian processes, this is just our model here. Okay. Y is c of x, a line through the origin, where we pick the gradient randomly from this normal distribution. Well, the first thing to note then is that the expected value of y of x is 0. And if we look at the covariance between y of x and y of x prime, that's the covariance between c of x and cx prime. So the x's come out here because they're not random. So it's the covariance between c and c. It's the variance of c, which is 1. And so we get the covariance here is x times x prime. Okay. And obviously here, if c is Gaussian, y is Gaussian. So this is a Gaussian process. It's not a very interesting Gaussian process. In fact, it's what we call a degenerate Gaussian process. And that is, there's only really one bit of randomness going on here. But it's a Gaussian process, and it is a Gaussian process of lines. So this is what we call the linear covariance function, and it just generates straight lines through the origin. So in some ways, we can think about Gaussian processes as generalizing linear regression. We might talk a little bit about that in a while. Okay. Okay, so why do we want to use Gaussian processes? You know, in some sense, it's quite a restricted class of models. So there are other classes of models. Why are Gaussian processes useful? Well, it's all the properties we said about Gaussian distributions. That makes them nice. So if y has a Gaussian distribution, then if you multiply it by some matrix, you get another Gaussian distribution. Yeah, and all that's changed is you multiply the mean and the variance by something. Yeah. So it's nice in that sense. You can scale them, stretch them, do things to them, shift them. It doesn't change them much. So this in particular means that sums are Gaussian, and marginal distributions are Gaussian. So if you've got a long vector here, we just pick out some elements, it remains Gaussian. Okay, if you just look at the first element, that is a Gaussian. Okay. Let's skip that. The next property, and perhaps the more important property, the reason Gaussian processes are so widely used, okay, is that conditional distributions are still Gaussian. Okay, so let's suppose we've got a bivariate Gaussian here. We've got a multivariate Gaussian distribution, so just two values, y1 and y2. And that these have a multivariate normal distribution in 2 dimensions with mean vector mu, which is mu1 and mu2, and covariance matrix sigma, which is given by this here. Well, in that case, we can work out, and we might show in a moment, that the distribution of y2 given y1, so if someone comes along and tells you the first element here, someone comes along and tells you that y1 is equal to little y1 here, what do we now think about y2? What's that, now our model of y2? Well, it turns out that it's still Gaussian. We started off with a Gaussian, and we end up with a Gaussian. And all that's changed is we take the mean we originally had. So we originally said that y2 had a mean of mu2, so I can't highlight that here. And the new mean becomes mu2 as before, plus a bit. And the plus a bit is how surprising y1 is, how different it is from its mean, scaled by its variance. Okay, so just, you know, whenever we have a difference between a random variable and its mean, we need to know if it's a big difference or not, and that's what this scaling by the variance does here. And then times by how related y1 and y2 are, the covariance between y1 and y2. So if this is 0, if y1 and y2 are independent, then learning y1 tells us nothing about y2. It stays the same. But if they're strongly correlated, we get a big shift to this mean here. And similarly with the variance. The posterior variance, you know, the variance of y2 given y1 is the variance we started out with here, y22, sigma 22, minus a bit. And how much we minus depends upon the variance of the variable we observed and the relationship of the variable y1 to y2, the covariance terms. Okay. So I always think it's instructive just to see this proof once, just to realize there's nothing complicated going on here. So just a very quick sketch of it, and then we'll see it in general for Gaussian processes. And remember, we said that Gaussian processes are just infinite families of Gaussian distributions. So the math is exactly the same as here, essentially. So what we want to think about is the distribution of y2, given that we've observed y1. So that's just proportional to the distribution of y1 and y2, okay, where we're just going to ignore the y1 bit here. So if we write this out, we know that the multivariate Gaussian density is this quadratic here. So if I put the terms in, so we've got the variables y minus the mean transposed times by the inverse of the covariance matrix, which I've called Q here, times by this term again, which I've not written out here. Okay, but you've got it here. Okay. So it's just a quadratic in these bits. And all we care about in this calculation is the y2 here. So we want to see what does this mean for y2. So if we expand this out a bit, what we can see is we're going to get a term that is quadratic in y2 plus a term that is linear in y2. Okay. And you'll probably recognize this already. This is the shape of a Gaussian again. This is just e to the minus y2 squared plus a bit. Okay. So we started off with the Gaussian, we've looked at conditional distributions, and we end up with the Gaussian. So now there's a bit of tidying up to do to collect the terms, and go through this in your own time. I don't want to spend time talking about this now, I think, given how much we had of questions. But if you collect the terms in here, it's just simple algebra, and I really do encourage you to go through this once. Okay, you very quickly get to the right shape for the new mean and new covariance. Okay, so just by collecting the terms, completing the square essentially, so undergraduate exercise, you derive the right form. There's one tricky step at the end where you need a matrix inversion lemma, okay? But have a look in your own time, okay? It's worth working it through because it's the right way of thinking about Gaussian processes. It's just completing the square to get a distribution. Okay, so that's Gaussian distributions, where we just had two variables, right? I just had two variables here. Let's do it for Gaussian processes now. So let's suppose F is a Gaussian process. Then what we said was, if we have any finite collection of random variables from this Gaussian process, so for any finite collection of indices, so I've called them x1 up to xn plus an x, okay, so we've got n plus 1 values here. This has a multivariate Gaussian distribution with some mean and some covariance matrix. Now, let's suppose someone comes along and tells us the value of the function f at x1 up to xn. That's where we've collected data. Our data tells us what the value of f is at these n locations. Then what we've just shown on the previous slide is our belief, our distribution for f of x is still Gaussian. And all that's changed is we changed the mean and the variance. So we just take the expressions from the previous slide. So we'll look at expressions in a minute, but let's just look at the examples, the functions from here. I've got the plots that you'll see many times, I suspect, this week. you've got the prior samples here. So these are, like we saw earlier, these are just random draws from my unconstrained Gaussian process, random functions. Someone comes along then and says, well, I'm going to tell you the value of the function at 2, at x equals 2, at x equals 4, x equals 6, x equals 8, and x equals 10. So they've told us the value of the function at these 5 locations. And so now we're only interested in curves that go through these points. And so we can throw away, if you think about this kind of infinite range of curves, all the ones that don't go through those data points. So what we end up with is a Gaussian process model still, but now it knows about the data. So it's still a random curve and there's still uncertainty, but now at certain places it's constrained by the data. And so we get pictures that look like this. Okay? So there's still random curves. And the way we work out what the mean and the covariance function are is just by what we saw on the previous slide, which I'll spell out in more detail in a minute. Okay. So I think, yeah, I think I'll carry on. We'll take questions at the end, I think, unless there are any pressing questions now about things that are confusions. If anything's not clear, now would be a good time to ask those type of questions. Okay. So I'm going to come back to those 2 questions from Hong Bin and Felix later. Yeah, and Georgie as well. Yeah, thank you. Yeah, good point. But okay, if any kind of clarifications arise, please just interrupt me, Maurizio, on my. Okay. So the question is, why is f of x1 to f of xn in the first time belongs to n plus 1? Okay. Yes, so here, okay, it's because I've got n plus 1 values. I've got x1 to xn, plus I've got x as well here. Okay, so there's n plus 1 different values here. Does that make sense? Oh, and what is the dotted line? The question is here on this conditional update of the GPT slide. So what's this dotted line? I think that was the true function I used to generate the curve. Okay, yeah, I should have specified that. So the blue here is my posterior mean. The dotted line was the function I used to generate the curve. I wouldn't worry about that for the moment. Okay, so just continuing then. So I've said a bit of this, but just to reiterate, why use Gaussian processes? Well, it's because they're closed under addition. We can add them, they're still Gaussian processes. Most importantly, they're closed under Bayesian conditioning. So if we have some data, then conditional upon that data, f is still a Gaussian process. Okay, so if we observe the function in some locations and then think about what is our model now, we've observed the data, it's still a Gaussian process. All we have to do is change these mean and covariance functions. And the way we change them is just linear algebra. Okay, basic kind of linear algebra approach to changing it. So they are very simple mathematically to work with. And again, I suspect you'll see more of this later in the week. There's really nice properties. So if f is a Gaussian process, then any linear operator applied to f is also a Gaussian process. So you can differentiate them. The derivative is a Gaussian process if it exists. The integral is a Gaussian process. You know, a rotation is a Gaussian process. So they're just easy to work with mathematically. Okay, so let's just give the equations we need, okay, in more detail for how we do these updates. So again, we've got these endpoints here. We've got f of x1 up to f of xn that we're going to observe, and f of x, if you like, stands for the bits we don't know. Okay, this is going to be, we're going to work out the distribution of f of x given the other bits, and that will tell us what model we're in now. So if you think about the covariance function, covariance matrix, sorry, sigma for these n+1 points, it has this form. So we've just got the covariance between x1 and x1, x1 and x2 down to xn and x1. And then we've got the covariance between x and x1 and so on. Okay, so I've partitioned it in this way. And this top n by n matrix here, this is the covariance matrix. Your data, we often call this the gram matrix in statistics, or the kernel matrix in machine learning. I'm going to call that capital K of XX here. This is the covariance matrix of the data, if you like. Then this column or this row along here, I'm going to call lowercase k of x, and that is the covariance between x and xj. So the covariance between the function at this generic point x and the data where we observe the function at xj. Okay, so it's just this row here. So it's just some compact notation. Okay, this term doesn't change. So the slides we had previously, what does that mean in this general form? Well, it says that the distribution of f of x, given that we've observed the function at x1 up to xn, this has a normal distribution, or in other words, as a Gaussian process with this mean function m bar and this new covariance function k bar, where the new mean function is given by this row vector here, transposed, times the inverse of the gram matrix, times the observation. Okay, so f, bold f here, is the observed values of the function. Okay. So what is this? It is a vector times the inverse of a square matrix times a vector. So it's just linear algebra. Yeah? And we're good at linear algebra. We know how to compute this easily. Similarly, the new covariance function is just the old covariance function minus a vector times the inverse of a matrix times another vector. So just, again, linear algebra. And it's the same kind of calculation we can do here. So we can we're not going to do the inverse explicitly, of course, but we only need to do this. There's only one set of expense in this calculation here. We don't need to do the Cholesky decomposition twice. Essentially, we can share the cost between these two bits. Okay, yeah. So I've said that, I think. Okay. So in pictures then. So this is the kind of picture you'll see. So I've got 4 different observations here, and typically the kind of plots people give you are a plot of the new mean function. So the mean function started out at 0 here, and then I've observed the function in 4 places, and so I get a new mean function, which is this solid line m of x, and then I get a new variance as well. So people typically plot like a 95% confidence or credibility region here. And so that's given by the shaded region. So that's the mean function plus or minus 1.96 times the square root of the new covariance. This is the kind of thing we get here. And just note here that this is doing interpolation. We assume that we observe the function value precisely here. And so our posterior model should go precisely through these points, and that's what we get here. So this is what we sometimes call the no noise or no nugget model in statistics and geostats. So in practice, of course, we don't typically observe f of x directly. Typically, we observe y is f of x plus a noise. So let's suppose we have a noisy observation of f of x. Well, how does that change the calculation? Well, not much. Okay. So if we have data y1 to yn, which is the function value plus a bit of noise, then we still have that this vector is multivariate normal. And all that's changed from the previous slide is instead of having kxx here, the gram matrix here, we've now got plus a sigma squared, the variance of the noise, times the identity. So all we have to do is take the calculations we had before and replace k of xx by k of xx plus sigma squared times the identity. Okay. So the calculations we get look exactly as we did before. We just modify the term in red here.
Richard,
Yes.
there are a couple of questions that maybe need your attention.
Oh, please, yes.
So one by Felix. So in the current context, the prior is the GP with chosen M and K, and the posterior is the GP condition on some measured data, correct?
Yeah, that's right, Felix. So, so here we would have picked the mean function to be 0 in advance, and I think I picked the RBF kernel a priori. Okay. So K of x here would be the prior covariance function. Okay, the mean function I assume to be 0, so there's no prior mean here. And then this is the mean and covariance conditioned on the data. Yeah, thank you for that clarification.
The other one is by Randall. Is the conditional at the invariant to permutations ordering?
Yes, good question, Randall. It is invariant to the ordering of the data. Okay, so it doesn't matter which order you condition on, and typically we'll do it all in one go, but if your data is coming in sequentially, then it doesn't matter which order you condition on, at least not mathematically. Numerically, of course, there can always be headaches and numerical difficulties, but mathematically, no, it doesn't matter. Okay. Am I safe to leave the other questions till later, Maurizio?
Yeah, I think so.
Okay. So just a couple more slides then, and then I'll stop and take questions, and we'll wind it up. Okay. So this is what happens if we have a noise term on the data. Let's look at the pictures. So now, instead of interpolating, we now don't learn perfectly. So here I've got noise on the data of 0.1. So you can think about this. You observe the function here, but you didn't observe it perfectly. You observed it noisily. And so our model shouldn't be perfectly confident about the value of the function there. There's still some uncertainty left. But you can see that when we're near the data, the uncertainty is much smaller than when we're not near the data. Yeah. So near the data, we've learned, but we've not learned as well as we learned here, where we could interpolate. There's still uncertainty left over. And if we change this nugget from 0.1 to something smaller, the uncertainty shrinks near the points. And if we let it go to 0, we'll be back to the interpolation situation we had a moment ago. Okay. So this nugget will typically be, this standard deviation here will typically be something we estimate from the data along with the other parameters. Okay, I'm going to skip that. So just to finish up then, there's various other derivations. We're not going to get to any of them. That's absolutely fine. They were above and beyond in a sense. So let's just talk about the difficulties of using Gaussian processors, and then I'll take questions. Okay. So we said that the choice of covariance function determines what our space of functions look like. Yeah, if we have an RBF kernel, we get very smooth functions. If we have Brownian motion kernel, we get very rough functions. Okay, nowhere differentiable functions. Okay, and in practice, when we're working in a situation, if we know what space of functions the truth lies in, yeah, so the covariance matrix here determines the space of functions we're working in. If we know that space of functions, that's great. Gaussian process works well. But typically, we don't know the space of functions. We don't know all these properties. So typically, we have to do a bit of trial and error. Okay, or if you be more technical about it, you might have a training set and a test set. So you might train your data with a given kernel on your training set, and then make predictions on your test set to see how well it works. And we might try just a few different functions to get a feeling for what is appropriate in our situation. So if you're modeling climate data, on weather or temperature, a very smooth kernel might be useful, but if you're modeling it on rain, a very non-differentiable function. It depends on what kind of situation you're working with. We also then typically have parameters here. Okay. So this is the RBS kernel we had before, and I've written it now with two free parameters. We've got a length scale parameter lambda and a variance parameter sigma squared. And typically we're going to have to estimate these using our favorite approach. So maximum likelihood approach to estimating lambda and sigma squared is by far the most common approach for doing these things. Okay? But people do cross-validation, people do Bayesian inference, expert judgment. We could compare the empirical covariance matrix, for example, in the way suggested. There's lots of things we could do here. Okay, but as I say, maximum likelihood, picking the values here that maximize the likelihood of your data is by far the most common approach and the easiest approach that's used. But there's always difficulty in these things. A Gaussian process model is this very rich, complex structure on the data, and it can be hard to understand it sometimes. Okay. So in particular, they're not always identifiable. So, you can have, suppose you've got a Gaussian process that you're modeling on 0, 1. And we've got the simplest model we can think of, an exponential covariance function here with just two free parameters, a variance and a length scale, or 1 over a length scale here. Okay. Now, even as you get more and more data, an infinite amount of data, as you infill the number of points here, you can't consistently estimate both of these parameters. Yeah, there's non-identifiability here. There's confounding between these two things. You can consistently estimate the product, but you can't consistently estimate either one. And so we get in this difficult game we have to play where we sometimes have to put in our expert judgment and help force the estimates to help find good values of these parameters to model the situation well. So as well as those kind of identifiability problems, we also have this complex optimization problem. If you're using maximum likelihood, for example, we typically have a maximum likelihood surface to estimate these parameters that is quite flat and can be multimodal in places. Okay? And so the optimizer can often get stuck. So one of the examples I often give is a Gaussian process. This is from GPy with these 10 data points here. So here I've had a prior mean of 0, a covariance function, and then I've tried to optimize the hyperparameters to estimate them for these points here. Now, if you do this repeatedly, 9 times in 10, you'll get a nice curve like these. So these data are from a sine curve here. Okay. So 9 times in 10, you get an answer that fits with what I hope we get. Okay. But 1 time in 10, the optimizer roughly gets stuck, and you get a prediction that looks like this, because according to the likelihood, these two are about as likely as each other. There's not a great deal of difference. So it could be this wiggly curve that looks like a sine curve, or it could be a constant with a load of uncertainty. Now, obviously, if you're a modeler, you're going to like this solution if you think there's something smooth happening underneath. Okay. But you have to watch out for the situations where you get stuck in answers like this. Okay, so typically, we do things like run the optimizer multiple times, multiple start points. We put prior information on the parameters, or we just constrain them in some ways to be, in the ranges we want. And we do things that, feel like cheating, kind of from this nice, clean way of expressing how we do statistics, but are the kind of the dirty tricks that we need to make them work in some situations. Okay. So there's lots of other problems and so on, which you'll hear more about from other speakers during this week. So just to say really that, that GPs were once a kind of niche tool in statistics and then machine learning 20, 30 years ago, and now they become ubiquitous. You see them in all sorts of applied papers and theoretical papers, and they're being used in, the popularity of the summer school is testament to that in some way. So I'm going to stop there. So thank you for listening. I don't know if you want to take questions now, Maurizio, or delay them. I'm happy to carry on answering questions. Up to you, Maurizio.
Maybe we can do 5 minutes questions because we don't want to delay too much the coffee break.
No,
And
we need a break. Yeah.
Yeah, people are asking also for the slides, Richard.
Yes. Okay. I will. If you go to my website, Richard, there's a link you can share there for last year's, or they're the same as last year's slides essentially. They're future.
Oh, okay.
If you could post a link, I'll put
Okay.
the updated version in a moment. Okay.
Okay.
But
we'll update we'll upload the ones the one that you send us later. Okay.
Okay. So I'll sort that out. So the questions, and let me have a look. So there's a question about, is this epistemic uncertainty? So that's, Nicole, that's more a kind of philosophical question. So epistemic uncertainty relates to a lack of knowledge as opposed to aleatoric uncertainty. And I think that depends upon your point of view. So for me, as a primarily Bayesian statistician, yes, I think of this as epistemic uncertainty. But for probabilists, many of them just think of it as aleatoric, so kind of randomness. Yeah, that just depends on your point of view. The nice thing about probability is many people can have many different interpretations of it, and the maths remains the same. It doesn't matter your philosophical viewpoint, the maths remains the same. Okay, so I'm going to pick off some of these questions. So a question from Georgie about that the sigma squared I term isn't necessary for the kernel to be positive definite. So let's just get to that. Was it here? Well, it's here. Okay. So I didn't present this slide, but this term here, okay, this sigma squared I term isn't necessary for it to be positive definite, but numerically the errors grow. Okay, and so numerically having a term like this here helps stabilize the system. It's a form of regularization. So it can be useful numerically, but it's not mathematically necessary, but often is necessary in practice. Okay. Vezel, sorry, the first name, asked what's the relationship between the posterior mean and the kernel ridge regression estimator. I did have a slide on that actually, which I won't get into, but they're the same thing essentially. So in kernel ridge regression, we have a space of functions that we're interested in, our RKHS, and we typically try and pick the best function to minimize a sum of squared errors, penalized or regularized in some way. And it turns out that the ridge regression estimator is the same as the posterior mean in that case. Okay, so hopefully that answers your question. There's a question, is data observed with 4 data points and slide will not get 1 sample? No. Okay, so there's no samples in this plot here. Okay, so we've got 4 different data points, and they're just observations of the function at one particular location. Okay, then I've not drawn samples on here. This is a picture of the distributions across space. So there was one with samples, isn't there? Okay, so here's the one with samples. So here are samples from this posterior distribution over here that are consistent with this picture. Okay, so these are the samples consistent with this. So I don't know if that answers your question, anonymous attendee, but hopefully. So Simon asks, what if there are 2 points that share the same x value but different y values? Good question. So in that case, we know we must be in this situation where we've got a nugget term. We know that this cannot be the situation we're in. Okay? If we've got an observation twice at x equals 1 with different y values, we've definitely got a noise term. So we're definitely in this situation. So in that case, this is the mathematics that we're interested in. We've got a nugget term, a variance for each observation, and we just work through this process. Okay. A good question here about why GPs are called non-parametric if the kernel parameters determine the properties. So they're also called semi-parametric, right? Yes, there are parameters that we have to estimate in these things, but they're non-parametric in the sense that if you fix the kernel, once K is fixed and M is fixed, then they are non-parametric models. The amount of information you need to store grows the number of data points. That's the definition of non-parametric, if you like. Okay. Paul asked, did the x-axis change from the number of parameters to something else? So it changed from, sorry if this wasn't clear, Paolo, sorry. It changed from being, I wrote it as an index here, where I was thinking about it as a number of variables. And I just went from being the index being 1, 2, 3, 4, up to 50, to being a continuous value, index between 0 and 5, say. Okay, so this is the interval between 0 and 5 of the real line. Okay, so yes, it did change.
Richard, sorry, maybe one more question and we finish.
Yeah, okay, yeah. So Thomas then asks, how do GPs found modeling data with extreme values, price spikes? So I dare say there are extreme value versions that I'm not aware of, but generally you are modeling here with Gaussians, and they're not going to cope well with extreme values. You've got very tails that drop off very fast here. The underlying function, of course, can try and account for that by having sharp peaks in it, but again, that needs a non-parametric kind of, that needs a discontinuous, non-stationary function. So it's very difficult to work with sometimes these extreme values. But that's not to say there isn't work in this direction. People haven't tried. Okay. So I think we should stop there. Otherwise, we're just going to run into the next talk, and I'll give everyone a chance for a break. So perhaps you want to say when the next talk is, etc., Maurizio.
Yeah, many thanks first, Richard, for the excellent introduction to GP. Yeah, so we'll be back at 11. So that's 11 British summer time. So maybe 12 for some of you, for the talk on kernels by Nicolas Durand. Will you please stop recording, Richard? Thank you.